Hi, my name's Mr. Ray, and this is the second video in a three-part series on the giant greenhouse math mistake, a second look at climate change. And in this video, we're going to focus on what I found about carbon dioxide, radiation, and the greenhouse effect. And we're going to try to take a look at that and see how it applies to global warming. Now, what we know is that the sunlight comes to the earth. Sunlight comes in the form of visible light. It's absorbed by the earth. The earth then warms up and gives off infrared radiation, which is heat. So there are three ways that heat is transferred. One is by conduction, which is direct contact, so where the air contacts the ground, it can be warmed that way. The second way is by convection, where the air circulates and it can warm itself that way by touching the ground and then circulating upwards and warming the air above. And then the third way is radiation, and this is the one that we're going to focus on. We know greenhouse gases absorb some of that energy. Now, nitrogen and oxygen can absorb the infrared radiation. They can be warmed by contact, they can be warmed by convection, but they don't intercept the radiation. Greenhouse gases intercept radiation, and that would be gases in the atmosphere like carbon dioxide, methane, and water vapor, all intercept some of these infrared rays. And so carbon dioxide happens to intercept radiation centered in a strong way around a 15 micrometer wavelength. So the question is, how many molecules would it take to completely overshadow the ground, overshadow a square meter of ground, and absorb all the radiation at the 15 micrometer wavelength as it comes up off the earth, and completely absorb it? Well, each carbon dioxide molecule has what's called a kinetic diameter, or a diameter of 330 picometers. All right, pico is a very small fraction of a meter. All right, so 330 picometers is the diameter of one of these molecules. And so how many molecules would it take to completely overshadow 1 square meter of the earth? Well, turns out that it takes 9.18 times 10 to the 18th. If you have 9.18 times 10 to the 18th molecules of carbon dioxide above the ground, that will completely overshadow 1 square meter. Well, how far up do you have to go to get that? At today's carbon dioxide levels, which we're going to say today's level is about 405 parts per million, but we're going to go with 400 parts per million. At 400 parts per million, there's going to be about 6.674 times 10 to the 21st molecules in 1 cubic meter of air. All right, so there's a lot more molecules in 1 cubic meter of air. But what are the chances are, if the radiation's coming up from the ground, that it's going to strike one of these molecules? Well, it turns out that at 400 parts per million, 99.99% of that radiation that carbon dioxide can absorb is going to be absorbed in the first 14 meters of air coming off the ground. Okay? So at today's levels, this many atoms will absorb all of the available radiation within about 14 meters. If you go back to pre-industrial times, 200 parts per million, which is a little bit below pre-industrial. Pre-industrial is about 280. So at 200, let's go to 200 parts per million. Okay. The same number of molecules will absorb the same amount of radiation in 28 meters. First 28 meters off the ground. So the radiation's coming up. It's going to strike a carbon dioxide molecules. You know, the radiation starting here is going to strike one here, more strike here, and then some over here a little bit. They're going to strike at different levels, but 99.99% of it's going to be all soaked up, all absorbed within 28 meters at at 200 parts per million. If we take today's 400 parts per million and double it to 800 parts per million, the same number of molecules are going to absorb the same amount of energy within 7 meters. And so, in all three cases, the same amount of radiation is absorbed by the same number of molecules. Increasing carbon dioxide does not change the amount of radiation that's absorbed. And when I saw that, I was very surprised when I realized that. The second thing that we want to know is how much do each of these molecules get warmed? Well, each of the molecules gets warmed 1.43 degrees Kelvin. In other words, when a molecule absorbs radiation, it warms up. It gets energy, it increases its vibration, and it warms up. How much does it warm up? Well, 1.43 degrees Kelvin for each molecule as the radiation encounters it. At 200 parts per million, this many molecules absorbs all the radiation available. Each of those molecules warms this much. At today's levels, this many molecules absorbs all the radiation. Each molecule warms up this much. Double the carbon dioxide, this many molecules will absorb all the available radiation, and they'll each warm up that much. At each carbon dioxide level of concentration, the same number of molecules are warmed the same amount by the radiation coming from Earth. One thing that's said about this is that the carbon dioxide absorbs the radiation and then sends half that radiation back to Earth, warming the ground. CO2 absorbs, and by the way, the wavelengths that CO2 absorb represent about 8% of the radiation coming off the Earth. So let's say that CO2 absorbs 8% of the radiation coming from the ground. It returns half of that, re-radiates it back down to the ground, and that's said to warm the ground. At 288 Kelvin, okay, the average temperature of the Earth, it's given off 391 watts per square meter of radiation. 8% of that absorbed by CO2 molecules, and if 4% comes back down, then what we're seeing is about 15.64 watts per square meter coming back down to Earth. Does that warm the Earth? This is called back radiation, called thermal down surface, downwelling long radiation, infrared radiation in a downward direction, or thermal radiation. This is radiation coming from those molecules back down to the Earth. Does that warm the surface of the Earth? Well, the problem is radiation cannot warm, radiation can't increase the temperature of the ground, okay, unless the incoming radiation is greater than the outgoing radiation. So 15 watts per square meter from carbon dioxide is not going to warm the ground at all if the ground is emitting 391 watts per square meter. All it does is all it can do is slow the cooling, okay? So in other words, instead of giving off 391 watts per square meter that it never sees again, if you take these two numbers and subtract them, you see that the Earth gives off a net of 375.36 if you just count carbon dioxide, all right? Earth is still giving off infrared radiation. It's still cooling. Okay, it's just not cooling at a high rate. This is not raising the temperature. This is slowing the cooling. Now, you say, well, if it slows down the cooling, isn't that going to raise the average temperature? Well, here's the problem with that. Remember, the same number of molecules are absorbing the same amount of radiation at every level. So if you've got 200 parts per million, this many molecules is going to send back 8% of the same amount of radiation. It's still going to be 15.64 watts per square meter coming from carbon dioxide. At 400 parts per million, same number of molecules is going to be sending back the same amount of radiation, the same 8% radiation. Double carbon dioxide, the same number of molecules is going to be absorbing all of the 8% of radiation and sending back 4% of it, same amount sent back. So back radiation can slow the cooling, but it slows it the same amount at all of these concentration levels. Back radiation can slow the cooling. The ground will only be warmed if the back radiation, if the radiation coming from the atmosphere is greater than the radiation coming from the ground. Now that does happen. It happens when warm air flows over cold ground, then the air is giving off more thermal energy than the ground is, and that warms the ground. But in general, the Earth giving off 391 watts per square meter and carbon dioxide returning this much is not going to warm the ground at all. It will slow it down from cooling, but it slows it the same amount at all these levels because the same number of atoms is absorbing the same amount of radiation and returning the same amount of radiation. Okay, so we find that increase in carbon dioxide does not increase the amount of radiation that's sent back to the ground. Another common fallacy that I discovered is that the idea that only greenhouse gases can emit thermal radiation into space. The idea is that at the top of the atmosphere, you've got all these CO2 molecules, and they've absorbed and traded wavelengths at the 15, around the 15 micrometer wavelength. And if we increase the number of carbon dioxide molecules, then it's going to reach a point, it reaches a point in the atmosphere where when the little carbon dioxide molecule gives off its radiation, it can shoot it up without hitting another one and get it into space. Okay, and if you increase the concentration of carbon dioxide molecules, then you raise the altitude that the carbon dioxide molecules can shoot off into space, or shoot the radiation off into space without hitting another carbon dioxide molecule. And because it's at a higher altitude, it's at a lower temperature, and that means that the surface is going to have to heat up to compensate so that we can get rid of the same amount of radiation, so that we can still be in a radiation balance. Well, here's the problem with that. Carbon dioxide is not the only molecule that can give off thermal radiation. Now, greenhouse gases are the gases that can absorb thermal radiation. Okay, they can take in thermal radiation. So you got CO2, you've got water vapor, and you've got methane. Okay, you've got CO2, water vapor, and methane. They are the only gases that take in the radiation. Okay, but they are not the only molecules that can give off thermal radiation. In fact, all matter that has a temperature higher than absolute zero gives off thermal radiation. That means that when these absorb radiation and warm up, they immediately share that heat with nitrogen and oxygen and any other gas that they happen to bump into. They immediately share that heat with those, and then those give off the radiation. They don't necessarily give it off at the 15 micrometer wavelength. As a matter of fact, all matter gives off thermal energy in what's called a black body pattern, and that black body pattern is centered on a wavelength that corresponds to the temperature of the molecule. So it'll give off radiation in a black body pattern with a peak wavelength that corresponds to the temperature, to the average temperature. And so what happens is, yeah, carbon dioxide is absorbing 15 micrometers, but then it and any molecule that it shares that heat with will give off radiation at wavelengths other than 15. It may include 15, but it's in a random black body pattern. And the reason that it comes in this black body pattern is because of what's happening with the gases. When gases warm up, they vibrate and they collide with each other. And so those collisions produce all kinds of speeds, but the average speed corresponds to the temperature. And so most of the time they're going to give off radiation that corresponds to their temperature, but there are other times when a molecule smacks into a molecule and just goes very slowly, gives off radiation at this temperature. Hits another molecule, maybe speeds up to this temperature. And so there's a pattern here of radiation that's given off, and it's centered on a wavelength that corresponds to its temperature. So what's actually happening is that the greenhouse gases are converting wavelengths. They're taking in certain wavelengths, but they're giving off all wavelengths. It's almost like a banker. Let's say there's a banker, or let's say he collects $20 bills, and in response he may give you 2 10s, he may give you 4 5s, he may give you 21s. He may give you another $20 bill, but randomly he picks from all those. What's going to happen? What's going to happen is the 15 wavelengths, there's going to be a lot less $20 bills in circulation, but there's going to be a lot more of other denominations of currency in circulation. So this is going to create a deficit at the 15. Carbon dioxide is going to create a deficit at the 15 micrometer wavelength, but while it shares energy with all the other molecules around it, they're going to give off energy, and that's going to create a corresponding surplus at other wavelengths. Okay, so the radiation isn't really trapped. It's absorbed, but it's also shared by direct contact, that's conduction, with other molecules. And it may be radiated, but it's radiated in a black body pattern that's centered on the molecule's temperature. And we saw that when carbon dioxide absorbs radiation, it raises it about 1.4 degrees Kelvin. So the first fallacy is that only the surface of the Earth and certain greenhouse gases can send radiation into space. And that's the basis of the fear that if we increase the greenhouse gases, then they're going to have to send radiation up from a higher elevation, which is a lower temperature, and that's going to have to increase the surface temperature to compensate for it. But the problem, that idea is false, because greenhouse gases are not the only gases that can emit thermal radiation. They're the only ones that absorb thermal radiation, but they can share that heat with other molecules, and all atmospheric molecules can give off thermal radiation. So if the greenhouse gas is absorbing 15 micrometer wavelengths, and it shares that heat with all the molecules around it, those molecules are also going to give off that radiation, but they're going to give it off at a different wavelength, or possibly most of the time it's going to be at a different wavelength. So you're going to have a deficit in the 15 wavelengths, but you're going to have a surplus in the other wavelengths. The second idea is that greenhouse gases trap the heat. They don't. Greenhouse gases absorb the radiation, but they don't keep it. They share it with the molecules. They share the heat with the molecules around them by contact. So if we look at all the gases in the atmosphere, every gas in the atmosphere picks up heat. You know, the sunlight comes in and it warms the earth. Okay, it warms the ground. All molecules, nitrogen, oxygen, all the greenhouse gases can pick up heat from the earth by direct contact. That's conduction. All right? And then that heat can be shared with other molecules by convection and by contact as the molecules circulate, as the air circulates. So you have convection and you have direct contact or conduction. And so when the ground heats up, it warms all the air molecules, not just the greenhouse gas ones. Now, in addition to the conduction and the convection, the greenhouse gases can absorb radiation. some of the radiation. Okay, we saw that carbon dioxide absorbs 8% around the 15 micrometer wavelength. So some of the radiation so the air is warmed three ways. It's warmed by direct contact with the ground, by sharing that heat energy, by contact with other air molecules, and through convection and conduction. Really, these two kind of work together. All right, and then there are some molecules that also absorb radiation. But then all the gases of the atmosphere, whether it's greenhouse gases or nitrogen or oxygen, all of them give off thermal radiation in a black body pattern based on their temperature. Now you wonder how much heat sharing is going on here. Well, the average time it takes a carbon dioxide molecule to absorb radiation and then give off a photon is about 1 second. In that amount of time, that one carbon dioxide molecule is going to be hit by nitrogen molecules 5.92 times 10 to the 28th times, about that many times. Okay, that's 592 with 26 zeros on it. If you put 26 zeros on 592 with 26 zeros, that's how many times in 1 second the carbon dioxide molecule is going to be hit by nitrogen molecules. That doesn't count the number of times it's going to be hit by oxygen molecules, okay, by other carbon dioxide molecules, or by water molecules, or any other molecules that are in the atmosphere. But on average, because there's a certain percentage of nitrogen, this is how many times nitrogen molecules are going to hit that carbon dioxide molecule in 1 second. What does that do? Well, each time those molecules come in contact, some of that thermal energy is shared with the molecule that's impacted with. And so that's going to, when the CO2 molecule absorbs the energy and heats up a little bit, it's going to be hit this many times. It's going to have to share that warmth with all those other molecules. Okay? And so then those molecules are going to radiate thermal radiation in a black body pattern according to their temperature. So after a few collisions like this, all the heat that was gained by the carbon dioxide molecule is going to be shared with other molecules, and the carbon dioxide molecule and the other molecules are all going to radiate at their average temperature. So they're going to radiate they're going to give off thermal radiation, and some of that's going to go straight into space, and some of it's going to be absorbed by other molecules, other greenhouse gas molecules, and then that will be shared, and then that will be sent into space. So what's happening is heat is being transferred from the ground to the air by conduction, convection, and some radiation to greenhouse gases. That heat is then shared in the atmosphere, and the atmospheric molecules then radiated into space. All the atmospheric molecules give off thermal radiation into space. Some of the thermal radiation, though, is given off back down to the Earth. And so a study of this is called back radiation. And there was a study of back radiation done in 2017 by a scientist named H. Douglas Lightfoot and another one, Orville A. Mamer. Both studied back radiation. Measurements were taken at 12 locations worldwide. The highest radiation that was found, that was coming back down to the ground from the atmosphere, was 420 watts per square meter. 420 watts per square meter of radiation coming back to the ground at, now I'm not sure how to pronounce this, but I'll give it my best shot, quadrillion. See, I don't know how to say that as a quadrillion or quadrillion atoll near the equator. Okay, so that's near the equator. This is the highest amount of radiation that was coming back to the surface. Now, the average temperature there, the average high temperature of the ground, this is the highest amount of back radiation coming from the air. The highest temperature, ground temperature there, the highest average ground temperature is 88 Fahrenheit, which gives you 486 watts per square meter coming from the ground. Okay, so the highest amount of back radiation was at this location near the equator. It was 420 watts per square meter. So if this is the Earth, 486 watts per square meter is coming up from the Earth, 420 is coming back down. So you can see that's a net of 66 going up. Ground is not being warmed here. It's just being, the cooling is being slowed. The cooling that's of the heat leaving the Earth is being slowed down this much. And so the net effect here would be 66 watts per square meter. 420 cannot raise the ground's temperature when 486 is leaving. Okay, that's cooling. But you can see the relationship. What's being given off by all the molecules of the atmosphere are radiating thermal radiation down to the Earth. The ground is sending thermal radiation up into the air, or up in, some of it's going straight into space, some of it's going into the air. Some of it's warmth being shared by the ground to the air contact, ground to air contact. So the air is giving off this many watts per square meter. The ground is giving off this many watts per square meter. The lowest radiation that they found, the lowest amount of back radiation they found was at the South Pole. It was 96 watts per square meter. All right, watts per square meter at the South Pole. And the lowest ground temperature there, the lowest average ground temperature there is about -76 Fahrenheit. And when that lowest average ground temperature is giving off radiation, that's 117 watts per square meter. So you can see even at the coldest location, the radiation coming from the air back down to the ground is 96. The ground is giving off 117. If you do the subtraction here, it's cooling at a certain rate, okay? But this is not able to heat the ground when the ground is giving this off, right? So back radiation in the highest case is not heating the ground, and in the lowest case, it's not heating the ground. The only time it can heat the ground is when the air is actually warmer than the ground that it comes over, and that happens once in a while. But on average, that isn't what's happening. If this radiation is coming from every single air molecule is giving off thermal radiation, then the amount of back radiation that's coming back to the ground is a reflection of the temperature of the air column above the ground. Now the average air temperature, we said in the U.S. standard atmosphere, which represents the average of the whole Earth, the U.S. standard atmosphere, 250 Kelvin is the average temperature, we said, of all the air molecules in the atmosphere. Well, that would produce 221.5 watts per square meter on average of back radiation. The ground temperature is 288 Kelvin. That would produce 390 watts per square meter of infrared radiation coming up from the surface. So there again, you can see it again on average. On average, the Earth gives off 390 watts per square meter. 221.5 of that is coming back down to slow the cooling. So there's a net radiation here. So what happens? The Earth is being heated by the sun. That's how this thing doesn't just cool off completely. When the sun comes out, more radiation is coming from the sun, and that visible light is absorbed by the ground. That heats up the ground. As the ground warms, it warms the air. The air then at the top of the atmosphere is giving off radiation into space, and so you have atmosphere that averages 250 Kelvin. You have space that's very cold, maybe 3 Kelvin, okay, out in outer space. you've got atmosphere of 250 and you've got ground of 288. So what's happening? The sun is giving the ground heat. The heat is being then net transferred to the air, and then there's a net transfer back out into space. But the fact that we have a blanket of atmosphere helps keep us warmer, because there's less of a temperature difference between the ground and the air, and then the air sends its radiation out into space. Okay, so let's sum it up. All right, so at the highest measured location, you had 304 Kelvin temperature, 88 Fahrenheit, giving off 486 watts per square meter going up. Radiation coming back down, given off by the temperature of the air, 420 watts per square meter, which corresponds to an average atmospheric temperature above that location. The whole atmosphere above that location has an average of 68 Fahrenheit, which is 293 Kelvin. Okay? That's the picture at the equator. The average, all right, the average, we know the Earth's average temperature is 288 Kelvin. That corresponds to 59 Fahrenheit. 390 watts per square meter going up. Okay? 221 and a half watts per square meter coming back down, which corresponds to an average air temperature of minus 9.7 Fahrenheit. That doesn't mean the air next to the ground. That means the whole air column from the ground up to the very top of the atmosphere averages about 250 Kelvin. That's 250 Kelvin, minus 9.7 Fahrenheit. And then we have the coldest. All right, so we have the hottest, we have the average, and we have the coldest. So the coldest temperature, you've got 213 Kelvin at the South Pole. This is minus 76 Fahrenheit on the average coldest temperature. That corresponds to 117 watts per square meter going up. They measured 96 watts per square meter coming back down. Okay, and that corresponds to a temperature, air temperature above the South Pole of minus 94 Fahrenheit, or 203 Kelvin. And again, that's from the ground all the way up to space. The average temperature over the South Pole then is negative 94 at that location. So it makes sense if you realize that every air molecule is giving off radiation, thermal radiation, in all directions. If every air molecule is giving off thermal radiation in all directions, then the back radiation represents the average temperature of the atmosphere above. The atmospheric column above it is going to be giving off certain radiation that corresponds to an average temperature of the air that's above that location. So basically what's happening here, sun warms the ground then cools by radiating into some of it into space. Some of that heat is shared with the atmosphere. The atmosphere then radiates some of it into space, and then some of that radiation is returned to the ground, which slows the cooling. Okay? And so Earth then maintains an average temperature of 288. The atmosphere maintains an average temperature of 250, radiating into space. Well, the worry is that carbon dioxide molecules, if the concentration increases, they'll have to release, they won't be able to radiate until they're at higher altitudes. Well, that's true about the carbon dioxide molecule, but remember what happens. The carbon dioxide molecule absorbs radiation from the Earth, then it shares it with other molecules. Those molecules then radiate at different wavelengths. So the net effect, what's really happening is that the 15 micrometer wavelengths are being absorbed, but other wavelengths are being given off. So there's a deficit in the 15s, but there's a surplus in the other, there's a corresponding surplus in the other wavelengths given off by all atoms. So the carbon dioxide is taking in the 15s and giving off other wavelengths based on its temperature. It's also taking in the 15s, sharing some of that heat with other molecules, and they're giving off radiation, again, in a pattern that reflects their temperature. So instead of radiation being trapped, it's actually being converted from these wavelengths into other wavelengths. So there's a deficit. Wherever there's a deficit at these wavelengths, there's a corresponding surplus at other wavelengths. Now I'm going to show you a chart of this. Okay, this is a chart of the Nimbus 4 satellite radiation profile over the Pacific. And what this is, these are all the wavelengths. And you'll notice that there are some dotted lines here. There's some lines right here. This is at 300 Kelvin. That's the black body pattern of radiation given off for 300 Kelvin. This is the black body pattern that's given off for 290. And this one is 280. So those smooth lines that are on there show what kind of radiation pattern we would expect based on the temperature of the molecule of the air, basically the air temperature. Since this is at the top of the atmosphere, this is measuring the ground and all the air all the way up to the top of the atmosphere. And so you see these wavelengths here. Now you can see there's a depression right here, okay, and that depression is centered around 15. This is the 15 micrometer wavelength. This is where carbon dioxide is absorbing some of the thing. And so what will often happen with these charts is that they will highlight a line near the top of the chart. And so they'll see these the top of these lines of these radiation lines here, and they'll draw a line along the top of it like this, and they'll say, well, that's the surface temperature, okay, and it's just below 300 Kelvin. And then what they say is, well, this is where the greenhouse gases are trapping some of the radiation so that it can't escape. And if the greenhouse gases are more, it's going to trap more. So what you realize is that this line is the total amount of radiation that's being measured from the Earth and from all the air in the column below the satellite. All right, and if you add up all of the area underneath those lines, or underneath that curve, okay, it corresponds to this green curve right here. So that's the total, that's a sum of all of the radiation that's come up off the Earth to reach this satellite, is the green line. And what you then see is that, yeah, there's some deficits in the 15 area, but there's some surpluses in the other ones. If this is the total energy coming up off the Earth and reaching the satellite, some wavelengths are depleted, other ones show surplus. And that's really what's happening. Yeah, there's greenhouse gases that are absorbing and causing deficits of certain wavelengths, but they share the energy with other air molecules, which creates a surplus of energy in those wavelengths. So the net effect of a greenhouse gas is not to trap heat, it's to convert it from one wavelength to another. All right, and it converts it by absorbing that wavelength and then giving off other wavelengths, or sharing it with other molecules that give off other wavelengths in a random way, in a random pattern that corresponds to the black body temperature. So if we add up all of the area under this curve, that's the total temperature of the air column. Some of the wavelengths are depleted, other wavelengths have a surplus because of that conversion factor, that where the greenhouse gas is absorbing certain wavelengths, sharing the heat with other molecules, and then all the molecules are giving off a random amount, and so the whole process results in a deficit at some wavelengths and a surplus at other wavelengths. Okay, and that's really how the radiation is working. So what can we conclude from this study and from this video? If you increase the carbon dioxide concentration, you do not increase the heat in the atmosphere, because the same number of carbon dioxide molecules absorb the same amount of radiation, whether it's 200 parts per million, 400 parts per million, or 800 parts per million. You have the same number of carbon dioxide molecules absorbing the same amount of radiation coming off the Earth. Second thing to conclude, back radiation does not raise the Earth's ground temperature unless the back radiation is more than the ground radiation. So the back radiation has to be greater than the radiation given off by the ground. And that doesn't usually happen, that on average doesn't happen that way. On average, the ground is always warmer than the air column above it. And so there's always heat being transferred from the ground to the air. The one exception is when you happen to have a warm body of air come over cold ground. Then the warm air can warm the cold ground. But most of the time, and on average, the radiation coming back from the atmosphere is less than the radiation being given off by the ground. And so it doesn't raise the ground's temperature. Okay, third point. Only greenhouse gases can absorb thermal radiation, but all atmospheric gases give off thermal radiation. So the idea that only the greenhouse gases are going to be able to radiate into space is wrong. Greenhouse gases will absorb certain wavelengths, they'll share that heat with the molecules around it, and all of the molecules, including the greenhouse gases, will radiate into space in a black body pattern that corresponds to their temperature. And so they can all radiate into space. Okay, next point. All gases in the atmosphere are heated by the ground, okay? By contact, this is all gases in the atmosphere absorb heat energy from the ground by contact and convection, okay? Greenhouse gases also gain heat by absorbing part of the radiation that's coming from the ground. So all gases absorb heat by direct contact and convection. Greenhouse gases absorb some additional heat from radiation. Okay? All gases in the atmosphere share the heat that they've absorbed with other molecules by conduction and convection, by contact and convection. All gases then give off thermal radiation into space in a black body pattern based on their average temperature. Back radiation is a combination of the radiation coming from every air molecule, not just the greenhouse gases. Every molecule with a temperature higher than absolute zero radiates in a black body pattern that reflects its temperature. Since every molecule is radiating, the radiation that's measured is coming from every molecule. Therefore, it shows the average temperature of the air column below the measuring device, or above the location being measured. Some radiation goes from the ground directly into space. Some radiation from the air goes directly into space. The ground cools by transferring heat to the air, mostly, and by transferring some radiation into space. The air cools by radiating heat into space. All the air molecules radiate heat into space, not just the greenhouse gas molecules. So the main effect of greenhouse gases on radiation is this. It creates a deficit in certain wavelengths in the spectrum by absorbing those wavelengths. Number two, it shares energy with other molecules through contact. Thirdly, then, the same as every other air molecule, it radiates a black body pattern of radiation based on its temperature. And what all that does together is it creates a surplus it creates a deficit in the wavelengths that are absorbed and a corresponding surplus in the wavelengths that aren't absorbed. And that is the effect that greenhouse gases have on the atmosphere. They are not responsible for raising the Earth's temperature 34 degrees. We found out in the first video, that's fiction. 34 degrees of greenhouse gas warming is fiction based on a faulty calculation of black body temperature. to sum it all up then, when we look at a chart like this, we've got the radiation coming from the ground and the atmosphere up to the satellite. The total of that radiation corresponds to this green line. The area underneath the green line is the same as the area underneath all the jagged measurement lines. Okay, so that total area, that total radiation coming to the satellite corresponds to a temperature between 270 and 280 Kelvin. That's the temperature of the ground plus the atmosphere below the satellite. Now the wavelengths, you see a deficit in the greenhouse wavelength. For carbon dioxide, you see a corresponding surplus in other wavelengths that are not intercepted by the greenhouse gases. So you've got deficits here intercepted by greenhouse gases, deficits here where it's intercepted, but then it's shared with other air molecules, so there's a surplus in these areas that are not intercepted by greenhouse molecules. And that's the sum total of the effect that greenhouse gases have on the atmosphere. It basically depletes certain wavelengths and causes a surplus in other wavelengths. So those are the main conclusions from this video, and I hope you've enjoyed it, and I hope it's been informative for you. All right, we'll have a third video will be on the history of climate change and what may be causing global warming. Thank you for watching.